before. And he had 50 million viewers. That's a lot of people, right? So somebody you're going to learn about today is just as popular, all right? And his name is Sir Christopher Ingold. In 1935, Sir Christopher Ingold and his man Edwin Hughes studied nucleophilic substitution reactions of alkyl halides and related compounds. And they proposed there were two main mechanisms at work, both of them competing with each other.
But there's really four mechanisms.
That's true. That's true. What I would like to do is next Monday, even though it's not really like my responsibility, I'd like to go through all four mechanisms with you. And I'm gonna expand this PowerPoint to go through SN1, SN2, E1, and E2, because it's very important that you have a good understanding for it. It's very important you have an understanding of these four mechanisms. Okay, it's just as spectacular as Doug Henning. The two main reactions, SN1 and SN2. The S stands for chemical substitution, and the N stands for nucleophilic. Substitution, nucleophilic. And the 1 and the 2 represent the kinetic order. Okay? Sir Christopher Ingold, known for organic reaction mechanisms. And kind of with your nomenclature and then the order, the Kang-Ingold prelude, the priority of something, of a substituent, the priority of a carboxylic acid, the priority of an amino group, right? At a chiral center. So this guy is he has a long staff medal, the Royal Society. He has a Royal Medal of the Royal Society, and he was knighted in 1958. When he walks into your campus, you just move out of his way, right? Just like Paul McCartney, okay? Just like Paul McCartney. Ringo's my favorite. That's why I tried to find a picture of Ringo. Just like these guys. Paul McCartney's a knight. So this guy is one bad dude. He shows up, University of Syracuse, move out of his way. Batista, World Wrestling Federation, move out of his way. He's the king. This is how he got down. SN2, methyl group primary. After a while, we get to compete in between secondary. SN3. Okay? And this is what you're going to be experimenting with today. Okay? The SN1 reaction. The SN1 reaction has a carbocation intermediate. So its products form a racemate, a racemic mixture. Okay? The nucleophile can attack from the front or the back.
Professor, could you please step back? Yeah.
Go back?
That was very interesting graph, right?
There are other things. Go ahead.
You will send it to
This is
us.
what you pay for. You ask questions.
You will send it to us too.
Yes, sure. This for right now, primary. Then as it goes, isopropyl is rubbing alcohol is secondary. But now they can both happen here. And then at tertiary, the SN2 is not going to happen for various reasons. It's not going to happen for various reasons.
There's not enough space to get a touch the molecule.
Exactly. That is the main space. That is the main reason. The main reason. The SN2. The main reason, Mark, is that the nucleophile can only replace it from here, and there's a transition state. The SN2 is a transition state.
So if it can't touch the carbon, then nothing won't happen.
Say it?
If it doesn't touch the carbon, it can't happen.
Exactly. So that means we have to have an appropriate solvent for that to happen. Okay, that's
Okay,
great.
next page, like this.
I need a, yes.
Could you please go backward to that?
Sure.
I'm sorry.
Eight coding.
Another one, like one forward. I mean, forward. Forward. Another one. Yeah, here. How would you define two problems like beyond the square brackets? It's like stands for two hydrogen. What is that? Two
The
plus.
2 plus signs on top.
Plus.
This is the Greek symbol for delta.
No, to the right. Outside the
Two
bracket.
pluses. Yeah, outside the square
Yeah.
brackets. Yeah.
Oh,
It's pluses.
okay.
Two hydrogen.
Just by convention, especially when you go to graduate school and you're going to get your PhD in organic chemistry, this symbol, right? Miles will go on and she'll see that this symbol represents a transition state. In the same book that you'll have when you do your first year, first level in graduate school, you'll see Carrie Sundberg has this symbol for the transition state. It's just a double plus sign, which means transition state. It just means transition state. And the delta is the Greek symbol for this delta. It's a net positive charge. It doesn't form a carbocation, but this has the transition state. Okay. The effect of the nucleophile. The nucleophile takes part in the slow step only of the SN2. That makes it bimolecular. But not in the slow step of SN1. Therefore, a strong nucleophile promotes SN2, but not SN1. So SN1 doesn't really, an SN1 reaction doesn't really, it doesn't really matter. It's not really dependent on the nucleophile. The effect of nucleophile, which you'll see today. Weak nucleophiles fail to promote SN2 reaction. So I need something that's going to, I need a fighter. I need a nucleophile that's going to push its way into that molecule. It has to push its way into that molecule. And if there are things blocking it, if it's tertiary, it's not going to happen. Okay? So in SN1, the nucleophile strength is unimportant. SN2, I need a strong nucleophile. The effect of the substrate, the structure. The structure is important. Methyl halides and primary halides cannot easily ionize and undergo SN1 reaction becomes methyl, and primary carbocations are high in energy. They are relatively unhindered, however, so they make good SN2 substrates. Tertiary halides are too hindered. So something like this is too hindered to undergo SN2. This is going to go SN1. SN2 substrates, tertiary not suitable. SN2, this is not going to happen. It's not going to happen by SN2, it's going to happen by SN1. SN1, tertiary, secondary, they're unlikely.
This happens a little.
If silver nitrate is added to an alkyl halide, it is a good ionizing solvent. It removes the halide ion to give a carbocation. This technique can force some unlikely ionizations, often giving interesting rearrangements. The slow step of the SN1 reactions, solvation, okay? The solvent, we could also reflux. You might be able to reflux your reactants. Very polar ionizing solvents such as water and alcohols are needed for SN1. So the SN1 reaction looks to have a polar solvent because it's a first. The SN1 reaction looks to have a polar solvent because it's a first order reaction, and it normally just depends on you put this molecule into an appropriate environment. Less charge separated is generated in the transition state, SN2. Strong solvation may weaken the strength of the nucleophile because of the energy needed to strip off the solvent molecules. Okay, if I want to go to one of those fancy restaurants, I got a waiting list, right? I have trouble getting in. Okay, I want to go to those fancy discos. I have trouble getting in. I got to know somebody. I get online. I don't want to have to go to that trouble.
Well, isn't it more like putting a rock star in the middle of his fan club?
Yeah. There's two. I need his. I want an autograph. I want Doug Henning's autograph. I can't get to him. There's too many people around me. Okay. I'm gonna be. I can't fight my way through. Okay. A strong solvent is going to weaken the strength of the nucleophile. So if I'm using water, which is a polar molecule, okay, it's going to highly solvate my substrate, and I can't get to the substrate. Thus, SN2 reactions go faster in these strange type of solvents. Okay, these solvents, they have these weird names. Okay. The slow step of SN1 reaction involves formation of two ions. Salvation of these ions is crucial to stabilizing them and lowering the activation energy. Okay, chemists and physicists at this point, you probably know from chemistry too, they always talk about things happening in the ground state, or lowering the activation energy, or having this low delta G. And when you go on to take advanced organic, okay, then you'll talk about these reactions in terms of that. Okay? The solvent may be heated to reflux, affects the solvent. What's this? What does that look like? What kind of distillation is this? That's right. It's the same as this. Yeah. That's what Rob's class can do. Transition state. You laughing?
Oh, it's fine.
You laughing at my transition state? What reaction is this? Blotter.
SN1.
No.
What reaction is this? SN2. What type of molecule is this? It's a methyl something. It's a methyl chloride, methyl bromide, or something, right? Transition state. This is SN. Has a transition state. SN2. There's only one minor star. It doesn't have that double plus thing. Aprotic solvents. These are the more popular ones. Dioxide. Huh?
That one.
Which one?
That's a common one. Oh, and that other stuff.
Right.
This
This one you might see later. Looks like water, kind of, right? Right? Except these the hydrogen, that's the oxygen. Okay? So it's going to behave kind of like water. The bond angle is a little smaller than water, right?
But the important thing is there's no hydrogen.
This you'll definitely see later. You'll definitely see this one later.
He's not kidding. You're going to be like an all-Argo too. You use tetrahydrofluoride as a solvent. You use tetrahydrofluoride.
So for this one, I need a good ionizing solvent. A good ionizing solvent is required for this one. a less polar solvent.
Polar aqueous.
The rate of SN1 reaction is proportional to the concentration of the alkyl halide, but not the concentration of the nucleophile. Goes first order. The rate of SN2 is second order. So for SN2, I need a strong nucleophile and a weird solvent. I need a strong nucleophile and a weird solvent to occur. SN2, I'm going to have one of these aprotic solvents for this. SN1, first order. SN2, second order. The SN1 reaction involves a flat carbocation intermediate that can be attacked from either face. This results in a racemic modification, meaning that I can have something that rotates the plane of polarized light, D or L dextrorotary or levo-rotary. There are two forms of glyceraldehyde. One is dextro, levo, and it's RS. When it carries out an SN1 reaction, it no longer rotates the plane of polarized light because of the transition state. An SN2 reaction will produce a product that still rotates the plane of polarized light.
I'll get you that 20. I'll get you that 20 minutes.
However, there will be a complete inversion of configuration. So in SN1, there's a mixture of retention and inversion in the racemate. SN2, complete inversion. There are rearrangements that can occur. There are rearrangements that can occur for SN1. Did Dr. Clement discuss that? Did you talk about that? When I had this course, SN2, there's going to be no rearrangements at all. An example reaction taking place with SN1 mechanism is a hydrolysis of tert-butyl bromide. It's tertiary in water, a regular solvent you heard about, okay, forming tert-butyl alcohol. So I'm taking an alkyl halide and I'm making an alcohol. If I have a company that makes this, I make a lot of money, right? Rubbing alcohol. I'm making tert-butyl alcohol is also 2-propanol, okay, right? Formation of tert-butyl carbocation separation by a leaving group, the bromide ion. All I need is to put this in a good solvent for this to occur. This is something that I remember from 25 years ago. Is a hydride shift. There's a hydride shift and it's also a methyl shift. So if you didn't do this yet, you'll do this next week. If a protonation occurs, if I protonate something, if I add acid to something, I can dehydrate it. Normally, when I add acid to something, I have an excess of hydrogen, and I can grab OH, form water, and the water will leave. When that happens, I form a carbocation. This carbocation is secondary, tertiary, primary, Melba? That's correct. After a hydride shift,